Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In a previous video in this playlist, we looked at the notion of derived duality, and we saw how by introducing an Ext functor, we could restore exactness of the duality functor. So the duality functor in general is not going to be exact, but by adding this extra functor, it turned out that we could restore exactness. And what I want to show in this video is that this is actually part of fairly general phenomena, and you can generalize this theory. So what we're going to do is we're going to introduce derived functors and show how they can be used to restore exactness of certain functors. So to start with, I want to look at the Ext functor, but in greater generality. So not just for abelian groups or Z modules. So here we're going to consider more generally, f is going to be any functor from the category of R modules to the category of S modules, and we're going to assume that it's going to be left exact, additive, and contravariant. So this is very much like the situation of duality. Okay, so a simple example of such a left exact, additive, contravariant functor is of course the dual where you hom into Z. That's the dual for abelian groups. But more generally, what you can do is if you start with this category of R modules, okay, say right R modules, you can pick any R module N and you can hom into that R module N. This hom gives you an abelian group, so it'll be left exact since it's a hom functor, also additive, and it'll be contravariant because you're fixing this variable, so it's contravariant in this variable, okay, and it will give you some abelian group here, so it'll be from R modules to Z modules. And what I want to do now is to define certain derived functors very similarly to what we saw in that video on derived duality. Okay, so for any natural number I, we're going to define the right derived functor RIF, and it will be from the same domain, so from R modules to S modules. And the way we'll do it is we're going to follow the same procedure that we saw for derived duality. Okay, so if we have some R module M, what we'll first do is we're going to pick some projective resolution for that, P dot. Okay, and then we're going to forget the M, we're going to just look at that P dot, and we're going to apply the functor F. So remember, we're kind of replacing this M with this, in some ways, a simpler skeleton. Okay, it's simpler in the sense that you're using projective modules, but it is more complicated because it's now complex, not just a module. Okay, so we'll apply F to this P dot, and remember F here is a contravariant functor, so it'll look something like this. 0 goes to F of P0, goes to F of P1, and so forth. So here you've applied some additive functor to some complex here, and so you get some sort of a complex, and you can talk about its homology. So RIF of M is just the minus ith homology of F of P dot. Okay, so the 0th homology is the homology here, the first homology is a homology here, and so forth. And that's how we're going to define our right derived functor. So remember some things. Of course, this depends on the choice of this projective resolution, but one of the things that we know is that if you have a different choice of the projective resolution, you'll just get something that's homotopic to the original, so up to a canonical isomorphism, this homology group won't change, okay, or this homology module. Also, I guess if you define a functor, you should define it on morphisms as well. So suppose you have a morphism of modules, so some module to another module here, then how do you work out the derived functors for each of those modules? You take projective resolutions for each of them, okay? And the key point is that if you have a morphism of the modules, you can lift it to a morphism of the projective resolutions, and those lifts, they're all going to be equal up to homotopy. Okay, so they're all homotopy equivalent to each other. So they'll induce the same homomorphism on homology. Okay, so that's how you get the derived functor. Okay, so in particular, if you apply this definition of the right derived functor to this particular functor here, this hom functor, the hom into n, okay, so that Fn, if you do the ith right derived functor of Fn of m, we get what's called the Ext functor by definition, Ext IR of Mn. So the notation here looks a lot like what you have for the hom functor. Instead of hom R Mn, okay, you're going to replace the hom with an ext. And basically we fix the n, we take a projective resolution of the m, and then we apply this procedure to get that result. Okay, so the next question is, well, does this restore, can these derived functors restore the exactness of the hom functor? So remember, the hom functor here is only left exact. Okay, so let's look at the theorem which tells you how this actually works. Okay, so suppose we have now a short exact sequence of R modules 0 to m prime to m double prime. So of course, remember this f is a contravariant left exact functor. So if you apply f to it, all the maps will go in the opposite direction. So you'll start with f of 0 here is 0, f of m double prime is here, f of m is here, and f of m prime is here. This bit is exact, but this last map may not be surjective. So we're going to restore the exactness here by saying, well, even though that's not exact, that might not be surjective. If you continue this on by mapping to R1 of f of m double prime, so that's this one here, that will be exact. Okay, so there exists a connecting homomorphism like that. And then you can apply the R1 f m double prime functor here, and it's also contravariant, I should have added here. Okay, so it'll be contravariant. So this will map to R1 f m, which maps to R1 of fm prime. And then that's going to be exact. And then to make it exact, we continue onto R2 f m double prime and so forth. So that's very, very nice. And I hope that you can see that the way we'll prove this is very much like how we proved the situation for derived duality. Okay, so let me just remind you how that works. And of course, the tool that we want to use, this is one of the main tools in homological algebra, is the long exact sequence in homology. Okay, so remember, if you have a short exact sequence of complexes, you get a long exact sequence in homology. So what is that short exact sequence of complexes that we're looking for? So what we're going to do is we're going to take this short exact sequence here. And remember, to compute the derived functors, you have to take projective resolutions of each one of them. Okay. And one of the things is that actually when we do this, we have to be a little bit careful. We can't just pick it randomly, okay, to make the proof work at least, okay? So what we're going to do is you're going to pick projective resolutions of basically the n prime and the n double prime, okay? And then using those ones, we're going to show that you can create a projective resolution of m, which is rather nice in the sense that, well, of course, you'll get maps, okay? And the maps will give you actually a short exact sequence of projective resolutions. Okay, so that requires a little bit of work to do, but we saw that in the example of derived duality, and the same sort of ideas work to give that result. So here we have a short exact sequence of projective resolutions. Okay, now what do you want to do? So now what you're going to do is you're going to apply f to just the projective resolution part. So we forget that, we just apply f to it. Now, of course, for all those projective resolutions individually, when you apply f to them, they'll no longer necessarily be exact, okay, but they will be complexes. But what's rather nice is that even though you may lose exactness when you apply f to those projective resolutions, the rows that you get, which were short exact sequences, remain short exact sequences. And why is that true? So remember, if you have a short exact sequence, so that means that all the rows here will be short exact sequences. That short exact sequence ends with a projective because, of course, you've got projective resolution. So it ends with a projective. And remember, one of the things that I've shown you in a previous video on the extension problem in hom lifting is that if you have a short exact sequence that ends with a projective, then it's actually split exact. And once it's split exact, if you apply any additive functor to it, it remains split exact. Okay, so in particular, it remains short exact. So once you applied f to the projective resolution, you still get a short exact sequence of complexes. And once you have that, you can apply the long exact sequence in homology. And what that says, if you just go through the definitions, is precisely this long exact sequence. And that's how you can extend, you can recover exactness for this non-exact functor by extending it in this way. Okay? So there are actually lots of derived functors floating around. So you may think, well, there's quite a few conditions, and it seems a little bit funny. You've got left exact here and contravariant, okay? And what I want to show you is another extremely important derived functor, and that's known as the Tor functor. And this is a fairly specific functor, but I want to show you the general sort of setup which gives you this functor. So here we're going to look at another functor from R modules to S modules again, but this time we're going to assume that this G is right exact and it's going to be covariant and of course additive. Okay, so what's an example of such a functor? Well, hopefully you've seen this. If not, just take it as something that's given. Okay, if you fix any left R module, okay, here you have a left R module, you can tensor it with a right R module to get an abelian group. Okay, so that's something that you can do. Okay, more generally, if this is an RS bimodule and you tensor it with this like that, you will get an right S module when you tensor it with a right R module. Okay, I'm going to denote this by G subscript n. Okay, so examples of this include, for example, if you tensor over Z, okay, with the rational numbers, so the Z module, which is Q, okay, that's basically localization, okay, so where you just put denominators on the module, okay, so that's the module of fractions in that case. Okay, so that's an example of the tensor product. Another example is, for example, if you want to change from real vector spaces to complex vector spaces, you can have R here is the reals, okay, the field of real numbers, and then this will be the R module, which is the complex numbers, and in that case there actually you'll change from real modules or vector spaces of the reals to complex modules, or in other words, vector spaces over complexes. Okay, so there are two examples of tensor product. So in this case here, we're going to do something very similar, okay? We want to define the derived functor of this, okay? And it's going to go also from here to here, and it's also going to be covariant, as it turns out. And how do you do that? So what you do is you pick something in here, okay, M, and again, you take a projective resolution of that. Okay, you take that projective resolution, and the left derived functor of this, what's it going to be? Okay, what you're going to do is you're going to apply G to this P dot, just like you did before. Okay, and it turns out because you're looking at a covariant functor, that instead of coming out this way, it goes back. Okay, it's going to be 0 from the after the degree 0. Okay, so it's going to go back. So here you look at the ith homology of G of P dot. Okay, so the Tor, this is the derived functor that you get when you look at this particular right exact covariant functor here. Okay, so the derived functor of the tensor product is Tor, just as the derived functor of the Hom functor is Ext. Okay, so Tor, now you have a superscript R and a subscript I, so with this left derived functor we put the I down there, of Mn is Lign of M. Okay, so again, it's a bit similar in the notation to this Hom and this Ext. Okay, N is on the right hand side. Normally you have an M here. Okay, so you'll have a M and an N there. And in this case here, you can apply the same argument. Okay, so the things are going around in different directions. Okay, the maps go in different directions, but still you can use exactly the same proof that I gave here to get a long exact sequence. So let's see what form it takes now. Okay, so suppose you have a short exact sequence of R modules 0 to M prime to M double prime. Okay, so remember G is some sort of right exact covariant additive functor. So you can apply G to this and the arrows go in the same direction. G of M prime maps to G of M, maps to G of M double prime maps to 0. And this part here being is going to be exact since G is right exact. Okay, but it may not be the case that this injects into here. Okay, so how do you sort of re-establish, okay, this exactness? Well, you have to have an extra map onto the kernel. And to map onto the kernel, since the kernel could be non-zero, okay, the way you can recover exactness is you add in this derived functor L1 of G. So L1 G of M prime maps to L1 of G of M, maps to L1 G of M double prime, and there's a connecting homomorphism to here. And so forth. You can get this sort of long exact sequence. Okay, so that's wonderful that we can see that we can generalize this example of derived duality in quite a general sort of context, and really the proof is just the long exact sequence in homology, and it works out quite nicely. So one of the things that you may think when you're looking at this, and it's sort of also kind of clear in the notation, is when you look at this xirmn, you may think that the roles of the m and n, they shouldn't be so asymmetric. They're kind of dual to each other, these two things. So why is it that you fix the n, okay, and you think of it as a functor in m, okay? You also have a Hom functor from m blank, okay? And you can ask, well, can you talk about derived functors of that? Well, you can also do that. So you can also find derived functors, xirmn, as a derived functor of Hom rm blank, okay? So here, this is also left exact, but now it's no longer contravariant, it's covariant. And the only difference that you do here, and this is kind of the key point and why we do things a bit differently, is that here you don't use a projective resolution, okay? So basically the key reason why is that when you do Hom into a the reason why the projective resolution is nice, okay, so when you replace this with projectives, is because Hom from the projectives into blank is going to be an exact functor. So here, the key point is that Homming into an injective is going to be an exact functor. So what you need to do is that this, whatever this module is here, let's call it n, you have to replace it with an injective resolution instead, okay? But other than that, you just replace it with an injective resolution, then you apply this Hom R functor to the injective resolution, and the homology of that is going to give you the same Ext functor, in fact, okay? And there's quite a bit of an argument, unfortunately, to show that the two things give you the same result, but it's certainly true. Okay, so that's the basics of derived functors, so we can certainly define them now. And we also see that we get some sort of long exact sequence. But the other thing is that how do we actually use a long exact sequence? So that's what I want to do now, is to show you a very, very simple application, which is kind of typical of the theory. It's a result that you can prove in lots of different other ways, but it really illustrates, you know, more complicated examples that you can use. Okay, so here's a simple application. Okay, so we're going to look at a short exact sequence of abelian groups. And it's going to be actually just looking at the extension of one cyclic group with another. And the cyclic groups that we'll look at, they're going to correspond to two positive integers, m and n, and they're going to be the cyclic groups of these relatively prime order cyclic groups. So suppose you have z mod nz and z mod mz, and you write a short exact sequence like this, okay, where m and n are going to be relatively prime. Then I claim that this module in the middle, okay, is going to be the direct sum of those two, and in fact this splits. And now, of course, you can prove this in lots of different ways. You can prove this, for example, using the structure theorem for finite abelian groups, okay? But there's quite a bit of proof to that structure theorem, and you'll see that what I'm going to show you now is going to be completely different, a completely different way of looking at it. And it allows you to look, remember, this long exact sequence is something that you have for really quite general module categories, okay? You're not restricted to, for example, structure theory for a principal ideal domain, okay? So you can really use this for quite general module categories, okay? So this is a fairly standard sort of argument, okay? So remember, one of the key things that homological algebra is good for is studying short exact sequences and studying extensions like this, and in particular saying when something is split. So how do you check that something is split? So the way you do that is the following, okay? So we're going to take this eta, so this is a short exact sequence, and what we're going to do is we're going to look at the long exact sequence in Ext that you get from looking at the functor. Well, let's do this version 2 here. We're just going to Hom z mod nz into this sequence. Okay, so that's a covariant functor. We're going to fix this z mod nz, and we're going to Hom this into this sequence, okay? That's a covariant functor, and it's going to be left exact, so we Hom z mod nz into this z mod mz. We Hom the z mod nz into this e, and then we Hom this z mod nz into the z mod nz. That's exact, and to sort of have a longer exact sequence, which tells you more, you have to throw in this derived functor, which is x1z z mod nz into z mod mz. Okay, so that's what you have here. Okay, great. Okay, so what do we need to do? So remember, one way of talking about this splitting, remember, is that you want to split, for example, the identity map. Okay, that's you want to lift the identity map from here to here. Okay, that's the way that you check that it splits. Okay, so what's that mean? So you have an identity map here, which means it's the identity on the cyclic group of order n. Okay, that's inside here. And what you want is, you think of that as the identity from z mod nz to here. You want to lift it up to this E. So that's an element of here. And such that when you compose with this, so in other words, when you look at the image on here, you get the identity. So the question here that you're asking is, maybe I'll write it in a different color, is, does there exist sigma which maps onto the identity here? Okay. So another way to describe that is, well, it's the identity in the image of this map. Okay. And the key point, and this is really where you use exactness, okay? The image of this map is the same as the kernel of this map. Okay. So this means that another way to check whether it's in the image now is you just need to see whether when you look at the identity and you look at its image inside here, is it 0? If it's 0, it's in the kernel of this map, so it's in the image here. And that's actually a criterion for checking whether you can lift this identity to a splitting map here. Okay. So what we often do in mathematics is we talk about obstruction theory. So if you look at one of my earlier playlists on homological algebra, first glimpses in homological algebra, you'll see the notion of homology as obstruction theory. So what's the obstruction to lifting this identity to this map here? Okay, it lives inside here. If it's 0, the obstruction vanishes, we say, and then you can lift. If it's non-zero, then that's the obstruction. And this is, to a certain extent, the obstruction space. Okay, so really, to prove this fact that this short exact sequence has to split, okay, we've recouched it in terms of looking at the image of our identity under this connecting homomorphism and checking to see whether it's 0. Now, of course, unfortunately, this connecting homomorphism is the hardest to sort of like get your hands on in homological algebra. So unfortunately, usually, not always, but usually we try to avoid actually calculating this map if possible. And that means that, unfortunately, the long exact sequence isn't as useful as you would like, except when the case that you can actually say something about this group. So in this case here, it turns out that this group, rather nicely, is equal to 0. And since this equals 0, actually this will be exact, right? Okay, because that's 0. So that means the image is going to be 0, so you can lift. So the only thing to complete the proof of this fact that such an extension, short exact sequence, has to split is to explain why this is 0. And the way I'll do that is another argument. So this argument requires you to study these derived functors. So I guess one of the things that this means is that you shift a lot of study to studying derived functors like this one here. And for example, the fact that we want to know here is, why is this 0? Okay. So the reason why it's 0 is the following. Okay, I'm going to do a little bit of a trick. Okay. So what I'm going to do is I'm going to look at the fact that this is a functor in both this module here and this module here. And this is also going to be an abelian group. And it turns out that, for example, let's multiply an element in here by n. How do I multiply by n? Well, it turns out that to multiply by n in this abelian group, okay, what I do is I just multiply by n in, say, for example, here. That's going to be a morphism here. And since this is a functor in this variable, multiplication by n, that map here gives you a map on the x. So it gives you a endomorphism of this. But what is multiplication by n here? That's going to be 0. So multiplication by n is 0. Now, it turns out, of course, symmetrically, that you can also multiply by n here. Okay, if you multiply by n here, that will also give you multiplication by n on this whole module. But what is multiplication by n on this z mod mz? So since n and m are relatively prime, actually multiplication multiplication by n is going to be an isomorphism here. And of course, functors send isomorphisms to isomorphism. So multiplication by n is both 0 and an isomorphism on this group. So the only way that an isomorphism of something with itself can be 0 is if the group itself is 0. And that shows you that this is 0. So here I've used a little bit of a trick to study this derived functor. And this is kind of typical in what happens with homological algebra. Okay, so what you'll see is that you can try to eke out a little bit more information about the problem at hand. So here you're checking to see whether something splits, okay, an extension splits, okay. So you've couched in terms of homomorphisms, and now you've got some extra tools to try to check to see whether you can lift. You can do this hom lifting because there's some obstruction involving derived functors. And then it becomes a matter of, well, can you study these derived functors? And so there's a lot of techniques in homological algebra which allow you to do this, and so allow you to answer many, many problems in algebra and in other parts of mathematics. I hope you enjoyed this adventure in pure mathematics.